All right, so the first learning objective for our calculus work together is that you will be able to reason with limit notation and compute limits of functions. So let's talk about how to compute the limit of a function. We're going to start today with the functions that are well behaved. So the good news is for well behaved functions, evaluating a limit typically requires no more than substituting in the x value at which you care about the y value. So there's a place on the bottom of that notes paper for you to fill in these two examples. So, and you can look at these in the book too if you prefer to watch how the book explains it. So I've been asked to find the limit as x approaches 3 of the quantity x squared times the quantity 2 minus x. I can simplify that by replacing x with 3 and making sure I follow the order of operations. So you can see here I have replaced all my x's with 3's. I'm going to evaluate the exponent first, make sure I simplify what's inside the parentheses, and I get a result of -9. So if I had no problem computing that result, then that result is the limit. It's that easy. I'm not trying to mess with you. The interesting thing is what's going to happen later when we do have a problem making that computation. But here we had no problem. Similarly, example 4b, I can replace all of those x's with 2's. Just make sure I follow the order of operation. I get 12 divided by 4 to make 3. So here, no complications. Your most common complication is division by 0. The next other ones you might find are taking the square root of a negative number, or taking the logarithm of 0, or a negative number. The one that's going to come up way more than the others is division by 0. But here we didn't have a divide by 0 problem. Our result is the answer. So if you would look please at your paper that I gave you. So we were right here. We just filled in question 6. You look on the back, and there's a whole little section at the top about combining limits. I'm sorry, I just got the little sections turned around when I fixed this up. So these 4 problems here have to do with what we just said a second ago. If you have a well-defined function, then substituting in the x value you care about is how you can compute the limit. So it's your job now to compute those 4 limits. Those are well-behaved functions, or at the very least, they're well-behaved at the x value I asked you about. And that's all you need to know. So you're going to simplify those using substitution. So you can remind yourself about some of these, like what does cube root mean, what does secant mean. But there's no tricks here, no special calculus. You'll be able to simplify after making a substitution in. All right, and now we can talk about this section up here. It turns out that, at least at places where functions are well-defined, or are well-behaved, is what I meant, well-behaved, we can perform algebra on limits the same way we're kind of used to performing algebra on regular functions or expressions. So these are some examples. Big picture, if you want to find the limit of, for example, I'm here. If you want to find the limit of 2 functions added together, this is function f getting added to function g, that's the same as finding the limit of function f, finding the limit of function g, and adding them together. Here, if you want to find the limit of 2 functions multiplied together, you can find the limit of the first function, the limit of the second function, and then multiply them together. Same with division, as long as you don't accidentally divide by 0. Some other ones to know. The limit of a constant function is that same value. So think about this. This says, remember we said limits are y values. So this here is like saying, imagine you had the function y equals b. That's a horizontal line. The question is, what if I let x equal some x value? What's the y value going to be? Well, the y value everywhere is the same value, which is b. All the rest of them are, you can see, this is a combination of the multiplication rule and that constant function rule. So let's do one of the ones from the bottom of that page, and then we will let you try the rest on your own. And you're going to bring your work to class, and if you have questions or problems, we're going to make sure You get all your questions answered. So let's do letter D. I'm going to say that the limit as x approaches c of f of x over g of x is equal to, according to that table up above, the limit as x approaches c of f of x divided by the limit. I can do so much better. So I've written that a little more nicely. So the limit as x approaches c of f of x divided by g of x, the quotient, the limit of that quotient is the same as the quotient of the two limits. So I'm going to find the limit as x approaches c of f and the limit as x approaches c of g, and I'm going to divide the two. Well, I've been given those two values. The limit as x approaches c of f, I've been told, is 2. And the limit as x approaches c of g is 3. So final answer, 2/3. So try to apply one of those rules from that top table to finish up those three.